so let's get started. So welcome to today's colloquium, and it's my great pleasure to introduce Professor Ken Osato from Chiba University. So Ken has got a PhD in Tokyo University in 2019, working with Naoki Yoshida, and he got a JSPS fellowship overseas at the Institute for Astrophysics in Paris for 2 years. And then he got a short postdoc term as another JSPS fellow in Kyoto University. And in 2021, he got he's very junior, but he succeeded got a faculty position in Chiba University as an assistant professor. So yeah, so Ken has been working on cosmology and mostly working on landscape structure, but also he works cross correlation between landscape structure and cosmic micro background. And particularly, he has been effectively working on both theory side and observation side. And yeah, as I said, so ASIAA involved Subaru PFS survey. That's the big galaxy survey, international galaxy survey, and ASIAA heavily involved. And we are targeting emission and galaxy as a tracer of dark matter distribution. So our clustering property of emission and galaxy is not very well known yet. So he's working on a very important topic of that field. So based on hydrodynamical simulation, so he will tell us about clustering of emission and galaxies. Yeah, please welcome him first.
Okay, thank you very much, Teppei, for the kind introduction. So I'm Ken Osato from Chiba University. Yeah, I'm great honor to be here. Actually, my last visit to ASIAA was 5 years ago when I was a PhD student. So I'm very happy to visit here, and I'm currently very super enjoying the Taiwanese food so far. Okay, so today's talk, I will talk about the emission line galaxy, clustering of the emission line galaxy, especially the main target for the future spectroscopic survey, and we want to address the clustering property using the hydrodynamical simulation, so which widely used in the astrophysical context, but now we can use this tool in the cosmological context. So okay, let me first begin. Yeah, but before starting, I'd like to just share the excitement of the Euclid launch. Yeah, it was super successful. It's launched on the last Saturday at the local time. So actually, Euclid is a space telescope which will observe the 1/3 of the sky the main science objectives, cosmology, especially in the galaxy clustering and weak lensing. So Euclid is now sailing to the Lagrange point 2 now, but after that, after the engineering run, so we will start the 6-year survey, cosmological surveys in this topic, the galaxy clustering, weak lensing. So actually, in this talk is quite relevant to the galaxy clustering studies, which will be done with this supervised space telescope. Okay, so let me go on to the main topics of my talk. So this is great. Brief introductions. Probably you already know the history of the universe so we have established a standard paradigm of the history of the universe. So as you knew in the cosmology textbooks, so there is a beginning of the universe. Then we have inflationary error, and we usually start with the hot Big Bang phase. So we have there is a very hot cosmic plasma where electrons and photons and the species are interacting very actively. So after that, after a few tens of millions of years ago, so we can see the structure formation happens mainly driven by the dark matter, which exerts gravity, and now the tiny density fluctuations produced in the inflationary error can be amplified with the gravitational instability, which is mainly driven by the dark matter. So now we can see the the hierarchical structures in the current universe, as we see, even by eye actually. So we can also probe into the details by the optical large-scale telescope. So this is the standard history of the universe. But so we also found the big mysteries in the universe. So that is the so-called the dark matter and dark energy. That is so these are the dark sectors. So the energy of the universe occupied by this dark matter, which drives the dark gravity and can be a source of the gravitational instability. So this is, we know that dark matter can interact with the gravitational field, but other than that, it's quite mysterious. And the other dark component is the dark energy, which drives the accelerated expansion of the universe. The space-time will expand, especially in the later time, so in the less than 1 or so. It drives the accelerated expansion, which now leads to the several of the Nobel Prize, actually. So actually, what we want to know through the cosmological observation or in the modern cosmology, so our common big mystery to shed light on is to find the signature of or fully understand the physics of the dark energy, which can have impact on the geometry of the universe, and also dark matter, which is also the mystery component. We want to know what dark matter is. So that can be probed through the observation of the largest structures or structure formation and evolution. So that is the main science objectives of my talk, and also in the observational cosmology. So let me focus on one of the specific observable. So that is the galaxy clustering I just showed here. The critical challenge in modern observation cosmology is that we cannot see dark matter and dark energies because these two components do not interact with the standard electromagnetic field. So we cannot directly observe or detect dark matter or dark energy so far. So we have to rely on the so-called biased traces. Actually, so that is the astronomical object which can emit light, or so it can be detectable through the some observations. But the biased tracer should follow the underlying density field, so which can be sourced by the dark matter. Okay, one of the most fundamental such object is the galaxies. So because the galaxy is it's an assembly of the stars which are bright in the universe. Also, there are many such of the millions of the trillions of the galaxy in the universe that we can use the galaxy distribution as a tracer of the underlying the dark matter or the density distributions. So that is the key idea of the galaxy clustering in the modern observation cosmology. So actually, this idea was realized in the last decade. So this is this is the last latest result by SDSS both survey. So this is this cloud is actually each of the actually there are millions of the points here. So each of which correspond to the galaxy. So we can measure the distance and also of course the angular position through from the telescope. But we also measure the distance, the line of sight distance. Then we can map out the 3D distribution of the galaxy through the spectroscopic survey. So that is one of the very striking results in this decade. Then we can also we can measure the statistics of the galaxy distribution, because the galaxy distribution itself has it's very difficult to extract information the galaxy distribution itself. But we also we have to rely on the statistics, so which summarize the information of the 3D distribution of the galaxies. So that is So here, so they're showing the one of the most fundamental statistics, that is the correlation functions. Maybe to show actually I will show you in more detailed way. Right, but anyway, so that is you can see some peaks here. So that is somewhat exaggerated, but anyway, so you can see and so for different plot correspond to different galaxy or quasar samples. So we can see some peaks, and it's correspond around the common distance of the 100 megaparsec. That is now called the baryon acoustic oscillations. So the scale of the BAO, so we showed for BAO, is determined by the cosmic so photon and electron interaction in the early universe. So this scale is robustly determined by the linear theory of the cosmology. So actually, this BAO scale can be used to constrain the geometry of the universe. Then we can probe into the accelerated geometry of the universe. That is, so we can measure whether the universe expanding or shrinking, or in accelerated or decelerated manner. And this BO scale is measured by the several of the different galaxy samples. Actually, this is one of the examples measured by the both surveys. So this is a normalized of the Planck results, so CMB results, as a function of the redshift. So, for example, main galaxy samples and luminous galaxy sample and emission galaxies, which is the main topic of this talk, and also the quasar, so distant astronomical object, which is thought to be powered by the black holes. Anyway, so we can use this BAO scale to constrain the geometry of the universe. So that is the main key point of the galaxy clustering analysis. So that is the main business of the galaxy clustering, but actually the reality is not so easy, actually. So I want to explain some very important effect in the real spectroscopic measurement, that is relative space distortions. Okay, anyway, to begin with, I'm sure here the density distributions I'm taking from the n-body distribution, that is a nonlinear density field here, shown here. So you can see the very massive clusters. But so as we learned in the cosmology textbook, so there is no special direction in the universe. We can the universe is homogeneous on a very large scale. So actually, the statistics like its correlation functions or its Fourier spectrum counterpart is the power spectrum. So this is roughly correspond to the amplitude of the density field in the Fourier space. But that is quite widely used fundamental statistic to characterize the density field of the universe or large scale function. So due to the statistical isotropy of the density field of the universe, the power spectrum has only one argument here, so that is magnitude of the wave vector. So there's no directional dependence for the power spectrum. So then we can the power spectrum can be described as a simple the one argument function. So that is a very important feature of the power spectrum in the real space. However, in the real measurement, so the situation looks quite different. So that is because we measure this line side distance through the redshift. So redshift, so of course the change of the wavelength can be caused by the cosmic expansion, that is Hubble flow. So that is, we can create a correspondence between the redshift and the two distance from the Hubble flow. But in the real cases, actually, so we also have to consider the peculiar motion of the galaxy. Of course, galaxies also moving around due to the surrounding gravitational field. So we need to include some additional contributions which are sourced from the peculiar velocity of the galaxies. So that means the density, distance estimate can be distorted from the Hubble flow, and also we have another contribution from the galaxy peculiar velocity. So actually now, so we have a special direction, so that is corresponds to the z hat, so which just correspond to the line side distribution, because the line side velocity can distort the redshift estimate. Then we have to consider here this additional term in the power spectrum or any other statistics in the large scale structures. So as a result, actually the power spectrum has two arguments like here. Of course, one of the arguments is the magnitude of wave vectors, and also this is the directional cosine of the wave vector. So that is now the power spectrum has directional dependence with respect to the line side distance. So that is very important consequence of the real measurement. So we cannot distinguish between the Hubble flow and galaxy peculiar velocity. So we have to consider both of these terms together anyway. So, and as you see, the density field looks quite different. So as the very center of this figure, so we are now I'm now showing us a same density field, but in real space and redshift space density field. So there are two major effects in the redshift space. So that is Kaiser effect, because there is at this figure, so there was a massive cluster here. That means there is a very deep gravitational potential well here. The surrounding matter inflow towards the gravitational potential well. Now, actually in redshift space, so the matter is more get closer to the this gas cluster center. Now, so this effect can be observed as the enhancement of the signal at the large scale, especially in the line side direction. So, and the other effect, the another important effect in the redshift space is the Fingerhut effect, which is looks clear in this figure. So you can see some spikes like here or here at the very center of the density clumps, that is dark matter halos. Because in the dark matter halos, actually gravitational potential well is so deep. So now the galaxy motions in the dark matter halo is very, I'd say, biliarized. Such kind of biliarized motion can also contribute to this the very high velocity like here can smell out the small scale structures, especially on the small scales smaller than the dark matter halo larger scale. So that can be observed through the small scale suppression of the power spectrum as a thing of effect. So far actually the electric space distortion, so RSD, makes the situation more complicated so far. So we have to remove this actually, but now the RSD can have also the positive side effects. That is, so we can have access to the the velocity field information, because now the power spectrum has dependence of the angular directions, but this angular dependence has more provides us with more degree of more information about the velocity field, which cannot be accessible, directly accessible through the real space power spectral analysis. So that is quite complementary to the density field. Of course, we can also have information about the density field, but through the RSD, we can also have extra information from the latitude space power spectrum. So that is a key example from the figure from third case. So we can constrain one of the very important parameters of the growth rate. So this is the derivatives, time derivatives of the growth rate, growth factor. So which is known to be very sensitive to the underlying gravity theory. So for GR with lambda CDM, so we can already know that F is proportional to omega matter to the 0.55 or so. So now we can use this parameter to constrain the gravity theory, or more specifically, we can test or verify the GR, or even potentially, so we can exclude GR in the with the precise measurement of this parameter F. Yep, here. So this is the comparisons of the current constraints of the F parameter, which basically appears as this form F sigma F. But anyway, so this is basically F. And the F parameters can be considered with different points, with errors come from the different spectroscopic observation programs. So which mostly are limited to the less than 1 here. So we have more data actually, but anyway, so most of the data comes from the lower ellipses. And the different line corresponds to the different theory of the gravity. So red one is our fiduciary choice. This is the lambda CDM with GR. And you can see some dotted line or dashed line comes from the prediction of the modified gravity theory, like FR gravity or DGP or Gaussian theories. So actually, you can see the difference is clear at the higher ellipses. Actually, the first one, so this is done by Tepe. So it's can put a tight constraint on the F parameter. So higher than at the higher ellipses, this is 1.3 or something like that. Now we can the precise measurement of the F parameter at the higher ellipses can potentially exclude or attest or verify the general relativity theory. So now most of the future spectroscopic survey will target target at the higher ellipses measurement of the disk growth rate, or just measurement of the galaxy distribution to higher ellipses more distant than the latitude 1 or 2, or even 2. Yeah. Okay, so let me just briefly mention the observational side of the spectroscopic survey. So in the coming spectroscopic surveys, like I just showed you the figure of the Euclid in the first slide. So of course, and Tepe mentioned the Subaru PFS is also one of the upcoming spectroscopic survey in this decade. So this survey will target the specific galaxy population, which is now called as the emission line galaxies, shown as the ELGs. So literally says, so emission line galaxies are characterized by the strong line emissions, for example, O2 or O3 HR4 emission lines. So these emission lines come from the nebular regions or star forming regions of the galaxies. So that is good piece of the star formation activity, because these emission lines is sourced by the short-wave and massive OB type stars. So that is a good indicator of the star formation activities. So, in summary, ELGs are blue and star-forming galaxies, and a large number of the emission-like galaxies, millions of the galaxies, are expected to be detected in the future spectroscopic survey. So, the background, the physical background is that because we are now targeting at the higher resolution to 1 or 2 or something like that. So this is a figure from the very famous paper, the Madam Dickinson 2014. So this shows the history of the star formation activity or star formation rate density. So how active the star formation is in terms of the cosmic level. So actually, we are now targeting less than 1 or 2, which now corresponds to the so-called cosmic null epoch, where the cosmic star formation activity is the most active during the history of the universe. So now we are targeting here. So that means the star formation is active. So that means that many emission-like galaxies are expected to be detected in the future spectroscopic surveys. I just listed some of these. So Euclid and Subaru PFS, and here this shows the relative distribution of the observed galaxies by DESI and BOSS and Euclid here. So actually BOSS is the completed survey, which basically targeting at the lower SF, and DESI is now ongoing and now publishing first results. And at higher SF, so Euclid will observe the emission-like galaxy up to 1.8 or so. So this is also a summary table for the forthcoming spectroscopic surveys. So Euclid and DESI will cover the 1/3 of the full sky, which is the largest coverage in the today. And PFS has data sensitivities. Now so PFS will observe the galaxy distribution at highest resolution, let's say 2.4, which is a very unique point of the Subaru PFS. So, okay, now good. So we can just focus on the clustering of the emission galaxies. So that is a very straightforward way to proceed. However, the clustering of the ELG is not so well understood yet. So, so this is a result from the semi-analysis, one of the type of the simulations. So far, we have used the so-called LRG sample. This is also a type of the galaxy population. So actually, this stands for luminous red galaxies. It's quite direct name, but anyway. So this is a red, and the star forming is already finished, quenched galaxies. So far, so this the point of the LRG is it's how to say it's a quite well-behaved sample because LRG is hosted by a quite massive halos. And this is the old sample. The luminous, these galaxies are already realized. So that means we can approximate the inter-halo velocity distribution can be well approximated with Gaussian. So that's okay. So in a sense, actually, ELG is quite opposite to the LRG samples because this is blue and star-formed galaxies. So that means hosted by the quite young and relatively small halos hosting the emission galaxies. Okay. So, and here one of the I'm just showing here one of the key examples of the difference between LRGs and ELGs. So here I'm showing the left-hand side is more important actually. So this is the velocity distributions within the halo. So actually, as I mentioned, so LRG is already old enough. So the dynamics within the halo of LRG is already visualized. So that means you can see the radial velocity distribution can be well approximated with Gaussian. So you can see some peaks, but anyway, that is a quite small effect. However, so ELG has quite a different form of the velocity distribution. So you can see some peaks at the positive radial velocity, which directly correspond to the coherent inflow toward the very center of the dark matter halo, like this. So this peak, so now this dynamics of emission galaxies has to be modeled in the modeling of the latitude space power spectrum, because now the latitude space power spectrum has quite much information about the velocity field of the universe, and also this feature must be addressed in the modeling of the galaxy clustering of the ELG. As I mentioned here, actually the formation nature and the evolution or dynamics of the hosting halo, right? So LRG is hosted by older, the massive halos. ELGs are hosted by younger, and the smaller halos. So that difference also propagates to the statistics of the latitude space power spectrum, for example. So, and we are now using these ELG samples for the future spectroscopic survey. So now we have to carefully think about the clustering the emission of galaxies. So this is also one of the examples for the statistics. So that is very similar to the anisotropic power spectrum, but also now in the real the configuration space, the anisotropic correlation functions. It's a similar discussion holds here. The correlation function has also the gradation cosine dependence. So actually, we usually use this so-called multiple expansions. So like, it's convoluted with the Legendre polynomial. But anyway, the key thing in this expression is that L equals 0 and L equals 2, the leading order terms are already widely used. L equals 0 is the isotropic component of the this correlation functions, and L equals 2 is the leading order of the anisotropy. So that is quite has a more how to say dependence on the velocity power spectrum. So that is specific to the latitude space power spectrum. So that should be 0 in the real space. So anyway, for monopole moments of the correlation function for the red is LRG and the blue are ELGs. Okay, the form itself is quite similar. So we can explain the difference between these two samples can be just adding some just a galaxy bias. But anyway, so for quadrupole moment, that shows quite different shape of the quadrupole moment. So that can be that implies that we have to incorporate some additional effect of the this one. Okay, you can please go ahead.
So why is the velocity distribution for the ELG not symmetric? The radial.
Oh, asymmetry. Oh, you mean here?
So the place where you label coherent info that produce a symmetric radial velocity distribution.
Oh, that is because the radial velocity. Actually, this is the matter of the definition. This is taken from the radial velocity. The positive is toward the center, and if the galaxy is getting far, so escaping from the galaxy center, that means the negative radial velocity.
I see. So it's not along the line of sight.
Yeah, exactly.
I see. Thanks.
So this is axis is different. Okay. Thank you for the question.
Sorry, that distribution obtained from simulation or data?
It's from the semiotic. This is simulation, and from semiotic simulations.
And do they study how this non-Gaussian feature depends on the redshift?
Oh, redshift. So, sorry, I think remember that. But anyway, so they have some studies about the redshift dependence. But in the main, text in this paper, so they are focusing on one specific redshift, redshift 1 or 1.5, the typical redshift for the LRG and the ELG.
Sorry, I just want to mention, so for LRG, it's actually a similar component, it's just the fraction is much lower compared to Emission like Galaxy.
So this is, probably you mentioned here.
Yes.
That's true. Still the LRG is not fully visualized yet. Some components can be in the undergoing some visualization process, so that might lead to some excess of the infolding part. But escaping from the dark matter halo is quite rare, so we don't see for the LRG and the ELG at a negative velocity component.
So does this affect clustering at all? Because you're not measuring the transverse direction.
Oh, transverse side is actually here. It's So actually, this is radial. So radial axis like here, and azimuth are like here. So if you take this one, this one like here. Oh, transverse model is actually transverse velocity distributions is where it's quite random. The transverse distributions. So now the velocity distribution quite very similar to the Gaussian distribution. Okay. So let's proceed. Okay, so let me now talk about our motivation of this study. Actually, the current methodology about to analyze the galaxy clustering measurement of power spectrum correlation functions is largely based on the clustering of LRGs. So luminous and red galaxies are more well behaved. It is easier to model compared. Of course, it's still difficult, but roughly, yeah, relatively easier compared with emission of galaxies. So our key question is like this. So is the current methodology of the standard analysis technique still applicable to the emission of galaxies, which is a future sample in the coming data? And if not, how can we modify the theoretical models for emission of galaxies? Because we already see some differences between LRGs and emission of galaxies, LRGs and ELGs. Actually, one of the examples right here. So the hosting halos are younger for the emission of galaxies, and the halo bias can also have some additional dependence, like which is now called as assembly bias. So that can also have some impact on the modeling of the power spectrum analysis. And also, ELG have some coherent dynamics, which are now informing towards the halo center. In contrast, LRG do not have such a coherent motion. It's almost really described by the random bilinear motions. So that feature can lead to so-called velocity bias problem. This is possible. And the emission of galaxies are star-forming galaxies. The conventional technique, which can relate the dark matter halos to galaxies. So we have many of these, actually, abundance matching or constraint correlation function, etc., etc. Anyway, so abundance matching in terms of mass, which is widely used in terms of the n-body simulations or estimation part. So this standard technique may not work for the ELGs. So that might complicate the situation. Maybe we can think about more about the clustering of the ELGs. So maybe there's a potentially, so theoretical modeling of ELG clustering should be modified. So because the methodology is not established yet so far, so we can closely study the clustering of the ELGs, and it's also timely because now we are expecting more data from the Euclid and PFS and the DESI. So to this end, so we have used the so-called hydrodynamical simulations, which I will explain later. But anyway, so that is widely used in astrophysical context to study the evolutions, the formation of the galaxies. So, but now, thanks to the increase of the computation power, so we can now run the cosmological hydrodynamical simulation in the cosmological volume, which spans more than 100 megaparsec, which are now suitable for the studies of the clustering in a cosmological context. So, by using these hydrodynamical simulations, so we will address the property of the ELGs and where ELGs lead, how ELGs formed, and also the clustering property, which is a goal of our studies. And we want to use ELG as a biased reset and to extract cosmological information from the spectroscopic data. Okay, so let me show you example of the video. This is a video taken from the IllustrisTNG, which is one of the biggest hydrodynamical simulations today. So, and we will use this dataset. So this is TNG 300 spans 200 megaparsec on the side, like here, and we can simulate the largest formation and evolution of the largest structure, which is roughly driven by the dark matter distribution. And also, simultaneously, we also model the formation of the evolution of the galaxies. We can solve the star formation in the subgrid physics, and after that, stars form the black holes, and also can have a feedback effect as a supernovae or black holes. And this part also modeled in the gas simulation. And we want to we have some modeling for the magnetic field. But anyway, so we can have quite everything actually here. So we can have direct access to the stellar mass and luminosity and colors of the galaxy, which are direct observable in the real universe. We can directly compare the simulation results and observational estimates. So here I'm showing that one of the snapshots from the ELGs simulations, which are fake images from the ELGs simulations. You can see the spiral galaxies and the exploded galaxies like here. So at the first glance, maybe you might be confused at which is real or fake. So that is actually the fake images are generated from the hydrodynamical simulations. So we want to employ this very high fidelity quality of data, the simulation data, to simulate and construct a realistic mock emission line galaxy catalog. So that is one of the that is the method which we will use in this study. So actually I've shown you the fancy video, but actually so what we use is actually the assembly of the data points here, because the simulation is basically the n-body method. Actually the output basically the points are here, so maybe you can see kind of like clouds are here. So I'm just showing the mixture of the dark matter particle and gas particles can be described as blue clouds as the dark matter and the orange cloud as the gas, and you can see some red cloud at the very center of the dark matter. This is subhalo. So this is this corresponds to the star particle. But there is a caveat about this. Actually, this star particle does not correspond to each individual star. That is still quite massive than the individual star. So each star particle corresponds to has 10 to 6 or 10 to 7 solar mass, which is kind of assembly of the stars like this. So here I'm just showing one of the subhalos in the simulation. But anyway, so what we want to know is the emission lines from each galaxies. So we just focus on the star particles, which is the source of the emission lines, or just surrounding gases source of the emission line. What we want to know. So star particle, which has also quite much information about this. So each of which has metallicity and mass of at the formation time, and also formation time as a redshift. But anyway, other information also can be stored in the hydrodynamical simulations, like chemical components, etc., etc. Anyway, so
sorry.
Okay, please.
Is there the star particle including the stellar type?
Sorry.
Stellar type. What kind of the stars?
So the answer is actually no. So we have so this is each star particle has so just a total mass. So we can actually so thank you for question. I'm just going to explain what is the stellar component of this star particle. Actually, so that is each star particle has some 10 to 5 or 10 to 6 solar mass of the stars. And the component of the OB type stars or more lighter stars can be described by the IMF and the evolution talks, which also actually we post-process the stellar particles. Okay, so let me go on. So actually, I will we couple with the stellar population synthesis code, which actually the post-process the star particle for each star particle. So each star particle, so we have IMF is the initial mass functions. So how many stars are formed in the star particle as a function of the initial stellar mass? Of course, the massive stars are quite rare than the solar type star. So how many stars? The component of the stars can be described by the stellar IMF. So there are several types of this, but anyway, so we can fix one masses. And of course, this is the initial mass function. So that is the component of the determined just as the stellar the birth of the star particle. So we want to trace the time evolution of each star. So each star, actually this is described by the of course the calculation of the stellar evolutions. So now described by the evolution facts, or maybe you can this also called as the isochrons. So it also has some dependence on the redshift. Metallicity. So now, and also mass. So we can trace the evolutions of the mass and temperature, the function of time. And so we just evolve the stellar as the stars as a target redshift, which we observe the galaxies. Then we also have to model the nebula emission, because so we want to know what we want to know is the emission lines from the galaxies. So the line emission comes from the star-forming nebula region. So we also couple with the photoionization pole targeted with gravity in the nebula regions. So this is the emissions of the some representative line emissions like H alpha, O3, or H beta. So as a function of the age, yeah, and the different color corresponds to different metallicity. Yeah, it's now also depends on the chemical component of the each star particle. Okay, now we have building blocks. So then we assemble into the one specific result. So that is spectral energy distributions. So that is luminosity with respect to the wavelengths. So you can see like here. So this is, yeah, the combination of the stellar continuum and also come from the dust emissions. So you can see some continuum emission plus line emissions from the nebula regions. You can see some other spike right here. So we have included some line emissions and stellar emissions from the simulations. Now we have for each subhalo or galaxies in the ELGs simulation. That means the 205 megaparsec box on the side. So now we have thousands of the millions of the simulated galaxies in the one box. Okay. Then we now select ELGs using this data. Then we can just apply the flux cut for PFS or ELG, PFS or Euclid or DESI. Now we can, here, the orange points, each of which corresponds to the simulated ELG, the color coded by the strength of the line emission, the O2. And the background is a large structure, that is density field. So the distribution of the ELZ here largely follow the underlying the largest structure in the universe. Now, so yeah, of course, you know, the galaxies or subhalos are biased trace of the underlying density field. Now you can see the distribution of these ELGs quite largely follow the underlying distributions. Okay, that is basically the methodology how to construct the mock emission line galaxy catalog. But anyway, but we want to use this catalog as to make some prediction about the ELG clustering. Before that, so we have to validate our mock ELG catalogs. Okay. The straightforward way to do this is actually to compare with the real universe, that is observation estimates. So the first thing we should do is just to compare with the luminosity functions. So luminosity function is just you're counting the galaxies with respect to the luminosity. So that is the simplest observation estimate which can be readily available in the previous literature. So okay, so to do this, so we have measured calculated the luminosity functions for two specific emission line galaxies, H alpha and ELG, O2 ELGs. And here, I'm showing here just to plot the left-hand side H alpha ELG and right-hand side O2 ELGs. And you can see two different solid lines, orange and blue. So blue one, so these two from the simulations, so from the mock emission line galaxy, which I showed in the previous slide. So the blue one is that we do not consider the attenuation effect of the dust. So because the line emissions are quite sensitive to the dust attenuation effect, so we have to model this effect to yield better match to the observation. Actually, the orange one is the result from with the dust attenuation effect considered. So this is the H alpha ELG at redshift 1.5. So this green line, green point with errors from the observations. So now we can get better match to the between the simulations and observation like here. So ELG is also some similar feature. But anyway, so the uncertainty of the observation is quite large for the ELGs. You can see some offset between these simulations and observations. But anyways, now we can. So these two results are reasonably consistent between each other. Okay, now, so we are ready. Now we can use mock ELG catalogs to do some predictions and to study the clustering property of the emission line galaxies. Okay, the first thing, first action item for this is just to identify where ELG are located in terms of cosmic wave structures. So as you might part of it. So the cosmic entire body can be classified into the 4 different regions. So depending on the quite complicated criteria here, but anyway, so that is correspond to the nose region, filament, sheet, and voids. And nose roughly correspond to the dark matter halo regions, so it's a very dense and collapsed regions. And filaments are the connecting regions between the nose and sheets, in between the voids and filaments. And voids are regions where there is almost no matter nor galaxies. Okay. So as I just showed in the formation natures of the emission galaxies, so one of the expectations is that the emission galaxies are likely to unfold toward the more massive structures. That means so ELGs should be located at the filamentary structures. So in order to address this, so I just plot here the fraction of the position of the ELG found. So the blue one is the orange one is the HFI ELGs and O2 ELGs, but quite very similar features. So around 30% of HFI and O2 ELGs are found in the nose regions because some of the ELGs have already evolved in the massive structure, massive dark matter halos. So already evolved ones. So that is roughly correspond to the 30%. And the majority is actually more than 50% of the ELGs are found in the filaments, which it's consistent with our expectation. So now most of the ELGs are found in the filamentary structure now unfolding toward the more massive structures. And the rest of the ELGs are found in sheets and voids, but quite rare. So that is quite different from the mass fraction, the volume fraction. Actually, the mass fractions is roughly correspond to the LRGs or massive structures. Actually, most of the LRGs are found in nose region, more than 50 or 60%. That is quite different from the description, the feature in comparison with the luminous galaxies.
Sorry, could you let me know how this is different from LRG?
Yeah, LRGs. So sorry, I don't have figure here, but the LRGs, the fraction, most of the LRGs are found in the 60 or 70% for the nose regions, and the rest of the rest is almost found in 30% or less than 20% here, like here, and there are almost no LRG of sheet and voids.
Thank you.
Yeah, sorry, I actually have another figure of this, but anyway, in this case, I'm just plotting the LRG only. So do you have any other questions or comments? I just need to wait here. Okay, so let me continue. Yeah, from now on, I will want to present you how we can relate the galaxy to the dark matter halos. So the simplest way to relate the dark matter halos and galaxies is now described as so-called halo occupation distributions, shortened as the HOD. So this is quite simplistic formalism to relate galaxy with dark matter halos. So this is just the mean number of the galaxy as a function of the hosting halo mass. So okay, let me also explain about the background of how why we need some kind of the relation between dark matter halos and galaxies. Because the halo clustering can be obtained through the dark matter oriented body simulations, and also some analytic modeling of the halo clustering is available in the literature. However, the clustering, as we did in this work, actually the modeling of the galaxy is quite different from the halo clustering. The halo clustering is almost modeled by the dark matter gravity, but as you know, the galaxy is a form. It's a consequence of the astrophysical processes, so it is very hard to model in an analytic way. So anyway, so we can predict the halo clustering, but as a further step, so we need a method to relate the halo to galaxies. So this is a HOD. Okay, so that is why HOD is developed so far. So this is one of the oldest model of the HOD designed for the luminous galaxy ELGs by Genjen 2009. So the horizontal axis corresponds to the halo mass, and the vertical axis is the number of the galaxies, and the blue bands and the red bands correspond to the HODs, or two defined galaxies. Anyway, but anyway, you can see the red one like here. So the HOD can be decomposed further into the two classes, which is the central and satellite. So, okay, the literary meaning the central galaxies. So each dark matter halo can host the central galaxy at the very center of the dark matter halo. So now, but the dark matter halo can host a single galaxy at most. So of course, this is just a central. Okay. So actually, the massive halos can host a central galaxy with almost 100%, but less massive galaxies, this may not be known. Okay, almost 50% of the dark matter halos around the 5 times 10 to 13 solar mass can have the 50% of the probability of hosting the central galaxy. So that means that this curve shows the centrality. And the other populations of the galaxy in the halo is the satellite galaxies. So actually, satellite galaxies located not necessarily at the center, so can reside close to the center or just out the skirt of the dark matter halos. And massive dark matter halos can host as many as the satellite galaxies, and the number of the satellite galaxies increase as the power of the function, like here. Okay, so that is the standard picture of the HODs. Actually, most of the galaxies or just ordinary galaxies show us something similar of the HODs. Okay, so now let's look at the HOD of our emission galaxy. So here I'm showing I'm showing the two different components like here, the central galaxy HOD and the satellite HOD like here. Actually, the power law index of the satellite HOD is quite shallow because the ELGs are quite short-lived, so they do not survive for a long time. So they may extinct after the certain period. So even massive dark matter halo can't host not so many emission galaxies. So for central HOD, that also have some clear signature of the difference between the from the ELGs. There is kind of small bump of Plato-like feature around 10 to 12 or 25 or so. So this actually is this small bump actually represents a distinct populations hosting emission galaxies. That is, I just repeated that infalling low mass halos just correspond to the were responsible for this small bump in the simulations. Okay, now so we are dealing with the simulation. We have much information about the dark matter halos and the galaxies now, so which are not possible in the real universe. But anyway, we can go into deeper. So now we can decompose the central HOD using the further splitting the galaxy samples into the two different classes, which are now called as the disk central and the spheroidal central, which are divided according to the morphology criteria here, which are available in the IllustrisTNG simulations using the Barsh over total mass ratio. Well, centrally, so actually disk dominated, which becomes younger and still actively forming the stars correspond to the this red component. Actually, this red component just corresponds to the infalling distinct populations. Then the four massive halos, actually, this is occupied by the spheroidal. Actually, the star formation is less active. Still, they are doing some star formation, but less active compared with this population at the solar mass around 10 to 12.12 or 10.5. Okay, now let's look at the fitting of the HOD. So where we are using because if you have the fitting or some functional form of the HOD, so then we can use this HOD to predict some the statistics of the galaxies, because we know the halo clustering. So on top of it, so we can use the HOD, then we can make some predictions of the status of the galaxies. Okay, so here I'm showing two different models. The left-hand side is the model is developed by Jen 2005. So this is very standard and widely used one. It's composed of it's made up of the 5 parameters. So, but it's also designed for the luminous galaxies. It does not explain well the HODs of the emission galaxies. It's quite different from the pointer from the simulations and the solid line from the the fitting results. But we also considered the extended HOD model, which captured the other components like here, the peak around here. Then we can fit very well the HODs for the simulators of measured HOD like here. So we have to extend our HOD model by introducing a few of the 3 or 4 extra parameters, but we can now explain the growing functions, and this peak-like feature also can be explained in one single model right here. Okay, then actually, but so far, so we have focused on the HODs and the cosmic wave, but these are not a direct observable. What we observe is statistics, like the projected correlation function I will explain. So we have a galaxy in the simulation like here in the 3-dimensional box. But by projecting into the line of sight one specific direction, so we can now have a catalog in the angular space. So these projections smears out the RSD effects. Now, so the modeling of the clustering becomes easier. But some might lead to the loss of the information. But anyway, this projected correlation function can be used to constrain the HODs of the ELGs. So this is one of the examples from also this is from Tepe and myself and many colleagues in Taiwan. So I'm showing here the projected correlation functions for the O2 ELG directed by Subaru HSG. So actually the projected correlation function also can be measured through the imaging survey, actually using the narrowband observations. Then we can constrain the underlying the HODs from this observed projected correlation functions. Now we can construct some HOD models from the GH model and GEM models, as I showed in the previous slide. So the similar analysis can be done with our mock emission galaxy catalog. Okay, now let me also talk about this a bit busy thought. Okay, anyway, so this is the project correlation functions that are specifically for O2 ELGs. This is this blue and orange line come from the model predictions with measured HOD, which we measure directly from the simulations, which is actually not possible in the real measurement. But anyway, that can be used to how the halo model works or not, to study the works or not. Okay, and this purple points results from the simulations, and each model works better, which can explain the projected correlation functions for scales larger than 8 or 9 megaparsecs. You can see the GEM model is still so looks working at some level, but not so good at the smaller scale. Smaller scales, non-linearity is effective, so we can make a good prediction at small scales. Okay. The second classes of the results is the red and the green one. Green one is actually almost overlapped with the red one. But anyway, so now we make the parameters in HOD free. So we do not. So we make everything the free parameters and to constrain the HOD from the projected correlation functions. So now you can see the perfect match at even smaller scales. Now, so you can see it's down to up to the larger scale, you can see quite good fitting of the projected correlation functions. However, if you look at the best fit HOD, the best fit HOD looks quite different. So this green points and blue and orange points from the results of the simulations, but this best fit HOD with straight and dash lines, look quite different. So And basically HODs and the HODs measured in the simulation looks quite different. So that has a very important implication about this. So we can fit the projected correlation functions with making the making the parameters of the HOD free, but so the result is not so not so good compared with the simulations. So that means we have the projected correlation functions is not enough to constrain the HOD. Sorry from this one. So we need have to impose prior knowledge of the HOD parameters. In particular, so we are using this mock emission Galaxy cutoff. Then we can have some prior on the HOD parameters, which can also have some extra information in advance from the hydrodynamical simulation. Is a good way to proceed. Okay, so I have only a few slides to end. Okay, so I just want to show the ongoing analysis of the. In this case, we do not project. So we use the anisotropic. We use the information, the redshift to space power spectra. In this case, redshift to space correlation functions. So we are now doing the cosmology challenge analysis. So that is, so we can infer cosmological parameters from the correlation function of the ELGs as we do in the real measurement. But the critical difference of the from the real measurement is that we already know the answer because we have generated the simulation by ourselves. So that means we already know the cosmological parameter which are used in the cosmological simulations. Then we can directly compare the best fit or the critical confidence regions of the each cosmological parameters. So with the answer, then we can directly test and verify our theoretical modeling of the ELGs. So that is the objective of the cosmology challenge analysis. Okay. So we have tested 3 different kinds of models. I do not go into the detail of this one, but the model one is the Kaiser plus. This is the completely non-linear one, the simplest and quite computationally less expensive. And we also have a perturbation theory based model like here. So this is completely analytical, but we also have some additional terms for the non-linear calculators. And the last one, the effective use theory, that is now getting more popular. Okay, that's fine. Anyway, so now we are still doing some tests for this. So we can constrain the 3 of the parameters like this, the bias parameters. F, this is the most important one, which can also the indicator of the is a good indicator of the what's gradation theory can be effective in the real universe. So using the model 1 and the linear cases. So now we can, it's still ongoing project, but we are now doing the extensive test for all models I presented here. So please stay tuned. Okay, let me summarize. So the hydrodynamical simulation is really powerful too. Now, so we can simulate the cosmological volume with the galaxy, with realistic galaxies. Now we can simulate the real galaxy powers, galaxy spectra. So I mean the galaxy spectral energy distribution. So far I focus on the one specific population, emission galaxies. So that is the main target of the future spectroscopic survey in PFS and Euclid and etc. So the theoretical modeling should be tested again for the emission galaxy cluster. So, okay, the first thing which I just presented is the HODs. So HOD can be constrained with the projected correlation functions, but only the projected correlation function is not enough. So we can have some more information from the simulation, then we can robustly constrain the HOD from the projected correlation functions. So the last thing I just showed briefly, so that is we can use the mock emission galaxy cutoff to constrain the cosmological parameter, or more specifically, we can constrain the growth rate parameters, which can be done in the real measurement. Then we can test the theoretical modeling, which I showed in the previous slide. Now, still ongoing project, but we can get which model works better or not to reproduce the, especially in particular the correct cosmological parameters from the anisotropic correlation functions. Okay, so that's all I'm happy to take your questions. Thank you very much.
A question about, if I read it correctly, you discussed
discover an inconsistency between the emission-like galaxy category construct in terms of angular clustering and HOD measurement. Do we see that similar thing in the data that in Cabet's paper we also do this HSE emission-like galaxy, and we also try different combination of fitting? Do we see the similar inconsistency, or why do we see this inconsistency in your model, and do you worry about it?
Yeah, that is really good question which I want to understand. So yeah, actually I'm showing here the results from the base paper. So I'm not sure. Anyway, actually we also found a similar feature from the data also. Actually in this paper, so we have found that the GH and GEM, both of these models can fit the projected cohesion function very well. And also we cannot distinguish between GH and GEM model from the projected cohesion function. So actually the reduced chi-sphere, the physiometric between GH and GEM is almost very similar. And yeah, the similar actually but GH model is slightly preferred compared with the GEM model. So that is also we also found in our analysis with the mock emission galaxy catalog.
Can I add one thing?
Yes.
So, the biggest difference here under the simulation. In simulation, you know true correlation function through HOD. But this data, you don't know. Yeah, this HOD well constrained, but we don't know it's correct or not. It's not direct observable. It is the biggest difference. Yeah, very pretty, but this. Yeah, we just determine HOD to explain the spatial distribution properly, but it doesn't mean that it's correct. To be fair.
Oh, that is actually a very good point, actually. Because, yeah, as we saw in the next slide, actually, the GEM and GH, basically by eye, so you can fit everything. So, of course, we already know that GEM does not work very well for this. Actually, by eye, GEM does not work for this. By directly looking at the HOD. However,
These two models only different in terms of a central.
yeah,
component.
basically yes. We also changed some. But you are right. Yeah, basically only changing the central. So, but yeah, as you know, so this GEM model doesn't work for this. But both of the GEM and GH model can do better. Can fit the data very well. Data in this case, in the simulation data. So we can see is a clear preference for the GH model in the analysis of the projected cohesion functions. Yeah.
Thank you for your talk. I learned a lot. So I'm actually a follow-up question. So I'm curious. So for LRG, it actually worked, right? For the GEM and GH. So it's just an error function plus a power law.
Yeah.
But for emission-like galaxy, the relationship between the halos and the emission-like galaxy are more complicated.
Yeah, exactly.
Can you show the plot over here? So I'm just curious. So based on the GEM and GH, I'm just curious. So based on your measurement from the simulation, it actually requires 3 components, if I recall. It's a central,
central.
at around 10 to the 12.2, and then there's a tail, and then the satellite. I'm just curious if you include these 3 components in the HOD model, and then try to let the model to fit the projected angular correlation.
What do you mean by 3 components? You mean
if
central?
You have
Gaussian step function and the power.
Yes. Okay. I see.
If you include as many parameters as what you found in the simulation, whether or not you can actually capture this. That's my question.
Yes. So you mean that by extending more terms that might explain the projected cohesion functions?
Another way around, whether or not, like, if you use more terms model, then you try to fit this, and whether or not you will actually get a similar result as based on your direct measurement from the simulation.
Yeah. So, okay. In this case, yeah, we actually found, yeah, quite very, let's say, inconsistent results with the measured HOD like here. But as you see, yeah, maybe we yeah, as I said, we can test the more models, more, let's say, maybe the gem model also, even for gem models, the best fit HOD looks quite different from what we measured in the simulations. So something like this. So, yeah, we actually, but so in this case, we make everything free without any prior. But actually in the web-based ones, so this one actually, so we have already included some priors on the, yeah, some relation between the HOD parameters. So yeah, that might help. Actually, that might can get reasonable HOD. So that is a more way to proceed. So actually, yeah. Also, we can use the information from our results to put some prior information about the HOD parameters. Oh, yeah.
So I guess one possible way to break the degeneracy may be to get the stellar mass halo mass relation.
Yeah.
Is this possible to do?
Yeah. So we can directly measure the stellar to halo mass relation from the simulations. Yeah, that is yeah, for the emission radius so yeah, that's true.
Well, I'm asking in observation.
Yeah, in observations. Yeah. Okay. So yeah, if there is a data about the stellar to halo mass relations for emission and galaxy, yeah, it's still possible, I guess. Yeah, maybe we can use this to add such information into the likelihood of this. Then we can, yeah, now we have information gained from the stellar to halo mass relations, and we can better constrain the HODs. So we can better constrain the both of the projected quotient function and stellar to halo mass relation.
How do you think the halo mass will come from?
Yeah, yeah, that's true. So I don't have ideas just on that. Yeah, that is. In this case, we have what we have here is the stellar to halo mass. Maybe stellar mass. Yeah, halo. Yeah. Yeah, it's it's very challenging to answer this one. But anyway, so yeah, additional information about some flux to halo mass relation like this. Yeah, adding more actually is adding everything. So adding the every information which we can have is can help to robustly constrain the HOD.
You have two more questions. Yeah, let's quickly.
Yeah.
Two more questions.
Thanks for the nice talk. So, if I understand correctly, so we're expecting better consistency when you consider or do analysis on an isotropic R spectrum. Is that correct?
Oh, you mean the anisotropic quotient function?
We will have better consistency in terms of HOD, measured HOD versus your modeling based on analysis on an isotropic R spectrum.
Oh, actually, in this case, we do not use HOD for this model. So we just switch to the different modeling actually. So we don't use the HOD like here. So in this case, we are using the kind of the perturbation theory model or nonlinear model. So in this case, the HOD does not appear in this model. Actually, the HOD is so as we see so in the previous slide, actually the constraining HOD has a very big degree of freedom, so which in the anisotropic quotient function we have also another information about we also have to add some extra parameter to model the redshift space. So that might quite many parameters. So yeah, the HOD will be less constrained with the projected quotient function. Projected quotient function is better to constrain the HOD, I guess. Yeah.
So on the projecting, so the previous slide, and also yes, this one. So just to confirm, so the blue line and orange line in the left corner correspond to the previous best fit HV
Yeah.
model. Okay.
Exactly. Yeah, this one. So for the plot, I will just use this best fit HOD to make a projection about the projection of the projected position function.
Okay, so there are very strong degeneracy between the HOD parameters of the ELG because the best fit HOD parameter by fitting the projected correlation function is quite
Yeah, you are right. Yes.
one. So
HOD parameters are quite degenerate between each other. So that's why. So there might be a very possible the local minima about GSIs. So that's why. And also HOD tries to fit more on the smaller scales because the error is quite small at this point. So actually we have also on the figure by applying the scale cut for this. But anyways, the scale cut actually does not help so much actually. So we still have such kind of the inconsistent HOD. But anyway, as I said, the parameter degeneration of the very severe, so we have to incorporate. We have to priors on the HOD parameters. Actually, we actually in the paper also as well. So we also have included some HOD, the prior HOD parameters. So in this analysis, we have very correct or answer like projected position function. That's why we do not include any prior information to be clear. But really, in that case, we cannot reproduce HOD from the project solely from the projected position function.
So in your simulations, you have the H alpha ELG and O2 ELG. So why, when you're going to discuss about the halo mass, you only focus on the H2 ELG? Is there any reasons?
Oh, you mean the reason why we should focus on the H alpha and O2? Yeah. Okay, so these two are actually the targets of the spectroscopic surveys. Euclid. Okay, this one. So this is for the Euclid will target H alpha ELGs, and subarctic press will target O2 ELGs. But this is So we also have some information from the other emission lines, O3, H beta, etc. So we have data for the other emission lines. So in addition to H alpha, H beta, represented one, we also have emission lines which are thought to come from the nebula emissions.
Okay. Very short question. I'm very interested in biasing property of emission line galaxies. Are they described by linear bias, or you need a non-linear bias relation?
That is exactly what we are currently doing. So I'm also interested in this point. So we have a common interest anyway. So this is a linear bias model with a nonlinear power spectrum. This is actually the extended TNS model. In this case, P delta G, we have so one root order galaxy bias, B1, B2, BS2, B3 with local Lagrangian relation. But anyway, so now we are doing the test for this. So probably I can give
what is the typical value of linear bias?
Linear bias is very high, it's 2 or 2.5.
2?
Yeah.
But D equal 1.4 or
1.5.
And increasing the redshift bias may be higher.
Yeah. It's
so in this study you focus on redshift
1.5. Yeah. It's that's true. It's increasing functions for the redshift or emission radius. Of course, it depends on the selection criteria, but anyway, basically increasing function.
Okay, so we are done. So so Ken is here until the end of this week. So please talk to him if you have more questions.
Yeah.
So let's come to Ken.
Thank you very much.